Good day, viewers. Welcome to Fame Global Academy. My name is Mr. Michael Osai, your chemistry instructor. Today, we'll be looking at modern electronic configuration using atomic orbitals or blocks of elements. And also, we'll be looking at how this particular topic is being applied as regard JAMB questions. But before we proceed, let's quickly look at what we mean by modern electronic configuration. How do we define electronic configuration? Electronic configuration is simply defined as the arrangement of electrons around the nucleus in atomic orbitals. It's simply the word, the arrangement of electrons on atomic orbitals around the nucleus. Before now, we had old ways of writing electronic configuration. We are not going to be looking at that this morning. What we have on the board says modern way of writing electronic configuration. What do we mean by atomic orbitals? They are the regions in an atomic structure where electrons are found or situated. We equally call them blocks of elements. We have four blocks of elements or atomic orbitals. We have the X block, we have the P block, we have the D block, and we have the F block. Again, what you should know at this point is that each of these atomic orbitals or blocks of elements, they have maximum number of electrons that they can occupy. For the X block or the X atomic orbital, the maximum number of electrons, that it can take or occupy is 2. So any value I write as a superscript value is indicating the number of electrons. Then for the p orbital, it takes a maximum of 6 electrons, while the d orbital takes a maximum of 10 electrons. Then the f orbital takes a maximum of 14 electrons. So from here, we can proceed to writing modern electronic configuration. We have a little should I call it chart that enables us to write this with ease. So you can have a representation like this: S, P, D, F. Then from this region, you can start taking it in this manner: 1s, 2s, 3s, 4s, 5s. Then for the P orbital, this first line, don't write anything there. Then start from the second. We have 2 here, of course. You repeat it 2, then everything here will be P. Then this is 3, right? 3P, 4P, 5P. And of course, for the D block, leave the first line, the second, then start from the third. We have 3D, 4D, 5D, then of course the F. We'll just write this, but there's no way we'll get to writing electronic configuration of elements that are in this block, because we are not expected to exceed the first 30 elements. So what do you do here? Leave the first column, the second, the third, then from the fourth to write 4F, then 5F. How do you pick these orbital? You pick in this manner. This progression is showing us the various energy levels from the highest energy level to the lowest energy level. I'll show you the application. Now, how do you pick? Let's take, for example, if you are told to write, give the electronic configuration of oxygen. How do you go about this? Very simple. Say, give the electronic configuration of oxygen. The first thing you should identify or know is what is the atomic number of oxygen. Of course, before now, atomic number is simply defined as the number of protons. It is also equal to the number of electrons. So it's the electron number we'll be making use of. The atomic number of oxygen is simply 8. So invariably, it simply means that oxygen has electron number of 8. So how do we write the electronic configuration of oxygen? I will know that the electron number is 8. You pick in this manner. Pick 1s. Mind you, I just said the maximum number of electrons that the s orbital can take is 2. So write 1s2. Then you pick in this manner. You have to write 2s2. This direction is showing us the movement from what we call the lowest energy level to the higher energy levels. Of course, before you get to the highest energy level, so you'll be picking them in that manner. But mind you, when you are picking it, you keep summing up the powers to ensure that it doesn't exceed 8 electrons or 8. Then after 2s we have 2p, we have 1s2, 2s2, then 2p4. So let's sum up now. We have 2 plus 2, 4, plus 4, that is 8. These are your write the electronic configuration of oxygen. Let's take an element that has a larger atomic number, like chlorine. Let's give the electronic configuration of chlorine. Of course, chlorine has atomic number 17. That is its position in the periodic table. So how do we give or write the electronic configuration of chlorine? We have 1s2, 2s2, 2p6, 3s2, 3p. Let me sum up the powers to ensure that it won't exceed 17. The atomic number is 17. Of course, it simply means the electron number is equally 17. We are talking about electronic configuration, so it's the electron number that we use in writing electronic configuration. We have 2 plus 2, 4, plus 6, 10, plus 2, 12. Then we have 5 left. You cannot write 3p, 5. This is the simple way you write or give the electronic configuration of chlorine. Then from here we'll proceed to how do we show the arrangement of these electrons in their respective orbital. How do we show the arrangement of these electrons in their respective orbital? The first one we wrote there is for oxygen. So I want to show you a diagrammatical representation of the 8 electrons that occupies the orbitals of the atom of element called oxygen. So let's show the arrangement of the 8 electrons. Now we've written the electronic configuration of oxygen as 1s2, 2s2, 2p4. How do you show the arrangement of these electrons diagrammatically? So let me teach you that now. This is 1s2. Now, this orbital cannot take more than 2 electrons. Each of the orbital cannot take more than 2 electrons. I'll show you what they mean by that. Then we have 2p4. 2p4 has 3 suborbital or share. There are rules or principles guiding the filling of electrons in orbitals. We have 3 rules, so I will name them. We have the one we call Pauli's exclusion principle. We have Aufbau's building up principle. Then we have Horn's rule. Now, these 3 laws or principles guides us or enables us to fill electrons in atomic orbitals with ease. Now we have on the board the electronic configuration of oxygen. How do we fill these electrons in each of these orbitals? For you to do that successfully, you must put into play these 3 rules or principles. I'll be taking them one after the other. The first one says Pauli's exclusion principle. In simple terms, Pauli's exclusion principle states that do not put more than two electrons into the same orbital but with opposite spin. I take that again. Pauli's exclusion principle states that do not put more than two electrons into the same orbital but with opposite spin. Let's apply it to this question that we are answering. Do not put more than two electrons into the same orbital. Do not put more than two electrons into the same orbital but with opposite spin. Now look at this orbital 2s2. Do not put more than two orbital. Do not put more than two electrons into the same orbital but with opposite spin. Let me correct something. Let's assume that the students have successfully written something like this. This is wrong. Why? The student did not obey Pauli's exclusion principle. Though he succeeded in filling this orbital with the two electrons, but because they are facing the same direction, it has defied Pauli's exclusion principle. The electrons must be filled facing opposite direction. That's what we mean by but with opposite spin. What's the application of Albert's building up principle? Or what is Albert's building up? Mind you, I'll come back to this. I'm here to feed this. There's a reason for that. Albert's building up principle states that electrons are fed into orbitals starting with the lowest energy level before filling those of higher energy level. What do we mean by from lowest energy level to higher energy level? 1s2 is the lowest energy level as seen on the board, followed by 2s2, while 2p4 is the highest energy level. That is what this principle is all about, Albert building up principle. Electrons are fed into orbitals starting with the lowest energy level before filling those of higher energy level. So to this progression, we are moving from a state of lower energy level to higher energy level. Now, of course, this one is the highest energy level for this particular atom of an element called oxygen. Horn's rule states that electrons are fed into orbitals singly first before pairing takes place in a degenerate orbital. What do I mean? Horn's rule states that electrons are fed into orbitals singly first before pairing takes place in a degenerate orbital. In a what? Degenerate orbital. In a degenerate orbital. What do we mean by a degenerate orbital? 1s is not a degenerate orbital. 2s is not a degenerate orbital. 2p is a degenerate orbital. What is a degenerate orbital? A degenerate orbital is an orbital that has more than one subshare. It simply means that the subshares, they share or possess the same energy level. The 2p orbital is a degenerate orbital because it has what? 3 subshares, and these subshares, they share or possess the same energy level. So for you to fill electrons in a degenerate orbital as we have in this 2p4, you must put into play Horn's rule of maximum multiplicity. What this Horn's rule states that electrons are fed into orbitals singly first. Let's feed these 4 electrons singly first before pairing takes place. Singly first, we have 4. We have 1, 2, 3, then 4. Singly first before pairing takes place in a degenerate orbital. Singly first before pairing takes place in a degenerate orbital. What's wrong with this representation? Let's assume that a student have written something like this. Maybe he or she wants to attempt filling these 4 electrons. And we're having something like this. 1, 2, 3, 4. This is wrong. When you see this type of representation, you can be asked, this representation contravenes which law? This representation contravenes Horn's rule of maximum multiplicity, because the student went ahead to what? To pair electrons in a suborbital without writing them or without representing them singly first